Welcome to Sleepy Stories. In this episode, we will take a clear and steady look at the Milky Way. This story is designed to help you rest while also offering calm and accurate scientific understanding. If you do not fall asleep right away, that is completely fine. You can simply listen and allow the information to pass by gently, knowing that rest can arrive in its own time. Before sleep comes, there is still space to learn something quiet and interesting about the universe around you. If you enjoy these stories, you are invited to like and subscribe, so you can return whenever you want to slow things down again. Simply listen, let your breathing slow, and allow the information to settle at its own pace. The Milky Way is not a distant destination or a place we imagine from afar. It is the galaxy we already live in. Every star you can see in the night sky belongs to it. Every familiar motion of the sun, the planets, and the seasons unfolds inside this vast structure. When we speak about the Milky Way, we are not describing something separate from daily life, but the larger environment that quietly contains it. From Earth, the Milky Way appears as a pale band of light stretching across the sky on clear, dark nights. For much of human history, this soft glow was observed without explanation. It did not move quickly, it did not change shape, and it asked for no attention. It was simply there, returning night after night. Today, we understand that this gentle brightness is the combined light of countless distant stars, seen from within the flattened disk of our galaxy. What once looked like a cloud is now known to be structure. A galaxy is a gravitationally bound system of stars, gas, dust, and unseen mass, all moving together over immense periods of time. The Milky Way is one such system, neither the largest nor the smallest, neither young nor ancient by cosmic standards. It has a shape, a rotation, and a history, all unfolding at a pace far slower than anything in human experience. This slowness is not emptiness, it is stability. The scale of the Milky Way is difficult to grasp, but it does not need to be imagined all at once. It helps to begin with something familiar. Earth moves around the Sun in a steady path. The Sun, in turn, moves quietly through the galaxy, following a wide orbit that takes hundreds of millions of years to complete. There is no sudden motion here, no sharp turning points. Everything follows long, smooth curves shaped by gravity. Most of the Milky Way is not made of stars at all. It is made of space between stars, filled with thin gas and fine dust. These regions are calm and diffuse, yet they play an essential role. Over time, they slowly gather, cool, and form new stars. Nothing rushes, nothing is forced. Change happens gradually, guided by simple physical laws acting patiently over time. The Milky Way also has a center, far from our location, where stars are packed more closely together. Around that center, the entire galaxy turns. This rotation is so slow that it cannot be felt or noticed in a lifetime, or even in many lifetimes. Yet it is always happening, maintaining balance across enormous distances. As this story continues, we will move step by step through the structure of the Milky Way, its motion, its history, and its place among other galaxies. There is no need to hold on to every detail. Understanding is not required for rest. Listening is enough. For now, it is sufficient to know this. The Milky Way is steady. It is structured. It has been here for billions of years, and it will remain long after individual moments pass. Within that quiet continuity, there is room to slow down. Simply continue listening, or allow your thoughts to drift, knowing that everything described here unfolds at a pace that never hurries. When we talk about the Milky Way, it helps to pause and be precise about what we mean. The name sounds soft and almost poetic, but in astronomy it refers to a very concrete structure. The Milky Way is a galaxy, a vast collection of matter held together by gravity. It contains hundreds of billions of stars, along with their planets and moons, as well as gas, dust, and a large amount of mass that does not emit light directly. All of this forms a single, slowly rotating system, with its own internal order and history. From Earth, this galaxy does not appear as a whole object that we can see from the outside. We are not looking at it the way we might look at a photograph of another galaxy. Instead, we live inside it. What our eyes notice on a dark, clear night is only how the galaxy looks from this embedded point of view. The faint, cloudy band that stretches across the sky is simply the densest part of the galactic disk seen edge-on, where our line of sight passes through immense numbers of distant stars. Seen this way, the familiar strip of light and the scientific idea of a galaxy are not two different things. They are the same structure, approached from two directions, one through direct experience, and one through careful measurement. The glow in the sky is what that structure looks like from within. The models and diagrams astronomers draw are what it looks like when its shape and motions are reconstructed in the mind. Being clear about this avoids confusion later. The Milky Way is not a flat picture that hangs above us. It is a three-dimensional system that surrounds us in every direction. It has thickness as well as length, and it continues far beyond the part that is bright enough to see with the unaided eye. Even when clouds hide the stars or city lights wash out the sky, the galaxy remains present. We are still moving with it, even if we cannot see it. For many people, the Milky Way begins as a memory rather than a diagram. It might be the first time they stepped away from a town, looked up, and noticed that the sky was not empty between the brightest stars. That impression of a soft, uneven glow can stay in the mind long after the exact details are forgotten. Astronomy does not replace that impression. It explains it. It takes that quiet experience and connects it to a larger, slower structure that has been in place for billions of years. In the background of daily life, the Milky Way is always there. It does not switch on or off when you pay attention to it. The motions of the stars, the slow turning of the galactic disk, and the gentle pull of gravity all continue at the same pace whether you think about them or not. As you listen, you do not need to picture the entire galaxy or hold its shape in focus. You can let the idea rest at the edge of your awareness, knowing that you are already inside the structure being described. The Milky Way is not something distant that you must reach. It is the environment that quietly contains every night, every season, and every moment of rest. This is why starting with a simple, careful definition matters. Once the Milky Way is understood as a real, physical galaxy that we inhabit, every later detail has a place to belong. Distances, numbers of stars, and long timescales become variations within a single steady picture. You can return to that picture whenever the information feels large. At its core, it remains the same calm idea. One galaxy, made of many parts, holding us gently inside it. On a clear night, far from city lights, the Milky Way does not appear suddenly or sharply. It emerges slowly as your eyes adjust to the darkness. At first you may see only a few bright stars. Then more begin to appear, filling the sky in all directions. Only after some minutes, when your vision has settled into the low light, does a soft, uneven band reveal itself. It stretches across the sky in a broad arc, brighter in some regions, thinner and more delicate in others. It does not have a hard edge. It looks like a narrow, pale cloud that never quite comes into focus. People who have lived their whole lives under bright, artificial light can be surprised the first time they see this band clearly. It can feel as if a hidden layer of the sky has been switched on. In reality, it is always present. The glow is simply too faint to overcome scattered light from street lamps, buildings, and illuminated signs. When that foreground light is removed, the older, quieter light of distant stars has room to be noticed. For most of human history, this soft band was part of the normal night. Before electric lighting, the sky was a consistent backdrop after sunset. The Milky Way arched overhead season after season, its general pattern unchanged. It did not rise and set like the sun, but rotated slowly with the stars as Earth turned. Different cultures gave it different names and stories, but the underlying experience was the same, a pale, flowing brightness that marked the sky more gently than any single star. Today, astronomy explains this appearance in straightforward physical terms. The Milky Way looks like a band because we are viewing the dense plane of our galaxy from within. When you look along that plane, your line of sight passes through immense numbers of stars at a wide range of distances. Each star is too faint and too far away to stand out by itself. Together, Their light blends into the diffuse glow your eyes register as a milky strip. Darker patches within the band mark regions where interstellar dust blocks some of that light, creating soft gaps and irregular shapes. The human eye has limits that shape what we see. It cannot gather light for long periods the way a camera can. It cannot easily separate extremely faint points of light from one another. As a result, the sky you see is a simplified version of the real distribution of stars. Long exposure photographs of the Milky Way reveal fine structures and intricate dust lanes that are invisible to unaided vision. Telescopes and sensors extend this even further, detecting light in wavelengths our eyes cannot sense at all. Yet the view from the ground remains valuable because it is direct. It is the simplest connection between the observer and the galaxy. Standing under a dark sky, you do not see the whole Milky Way. You see only the portion that happens to be above the horizon at that time of night and season. Earth's rotation brings different parts of the galactic plane into view over the course of a night, and its orbit around the Sun gradually changes which section of the galaxy is visible at different times of year. The band's position and tilt change slowly, but its presence is consistent. It is a quiet reminder that our planet is moving within a larger structure. Even if you are indoors now, and even if you cannot see the night sky from where you are, the physical situation is the same. Outside, above roofs and clouds and artificial light, the Milky Way is still present as a soft ribbon of accumulated starlight. It does not depend on being seen to exist. The stars continue to shine, their light continues to cross the vast distances of interstellar space, and the galaxy continues to turn at its slow, steady pace. The view is simply hidden by local conditions. Knowing this can be a steadying thought. The sky you remember from the darkest nights still exists, whether or not you are looking at it now. The Milky Way has been arching above generations before you, and will continue to do so for generations after. Its glow is the sum of uncounted distant suns, each following its own path, all held together by the same gravity that keeps Earth in its orbit. The band in the sky is not a separate object passing overhead, but a gentle glimpse into the structure that surrounds you all the time. To place ourselves inside the Milky Way, it is helpful to start with something familiar and then move outward step by step. The place you know best is the surface of Earth. You experience the cycle of day and night, the change of seasons, and the steady pull of gravity that keeps you anchored to the ground. All of these rhythms are connected to motions in space. Earth spins on its axis, turning you toward and away from the Sun, and it travels along a regular path around the Sun over the course of a year. The Sun itself is not fixed in space. It is a star, and like the other stars in the Milky Way, it moves within the galaxy. Our solar system follows a wide, curved path around the galactic center. This orbit is not fast in human terms. It takes hundreds of millions of years to complete a single circuit. In a human lifetime, the Sun advances only a small fraction of its galactic path. This makes our surroundings feel stable. The stars near the Sun change position relative to one another only very slowly, so the patterns in the night sky remain recognizable across generations. We do not live near the center of the Milky Way. The galactic center is a crowded, energetic region, where stars are packed much more densely than in our part of the disk. From our position, the center lies far away in a specific direction in the sky, hidden behind thick clouds of gas and dust that block visible light. Astronomers detect it using other forms of light, such as radio waves and infrared radiation, and by studying the motions of stars that orbit close to it. For everyday experience, though, it is simply a distant region that does not affect us directly. Our Sun is located in one of the galaxy's spiral features, in a relatively quiet stretch of the galactic disk. The distances between stars here are large. If you imagine the Sun as a small glowing ball, the next comparable star would be far beyond the scale of any ordinary picture. Space is mostly empty, filled only with very thin gas and occasional dust grains. This emptiness is not a flaw in the design. It is what allows stars and planetary systems to exist without constant disruption from close encounters with other stars. The environment around the Sun is calm on astronomical terms. There are no giant gas clouds pressing tightly against our solar system, and no very massive young star clusters close enough to flood us with intense radiation. This does not mean that the region is completely static. Over long timescales, the Sun passes through different parts of the galactic disk, encountering slightly denser or thinner patches of gas, and the background arrangement of stars shifts. Yet the changes are gradual. The solar system remains gravitationally bound and coherent as it moves. Being located in a relatively quiet section of the Milky Way has consequences. It provides a stable setting in which planets can form and maintain long-term orbits without frequent strong disturbances. It allows Earth to follow a nearly circular path around the Sun, receiving a fairly steady amount of energy over long periods. Life on Earth has developed and persisted within this context of stability. The galaxy does not control the details of life here, but it sets the larger framework in which that life unfolds. If you could pull back and view the Milky Way from a great distance, you would see the Sun not as a bright central beacon, but as one ordinary star among many, placed partway out from the center in the flattened disk. There would be no special marker pointing to our location. The spiral structure, the central bulge, and the faint surrounding halo would draw the eye more than any single star. From that perspective, our position is modest and unremarkable. From our perspective, inside the system, it is simply home. It can be reassuring to think of this placement in calm terms. We are not at a center that everything depends on, and we are not at a dangerous edge. We are carried gently along by the same gravitational field that shapes the paths of countless other stars. The Milky Way does not revolve around us, and we do not drift away from it. We are embedded in its disk, sharing its slow rotation, part of its structure in the same steady way that a single leaf belongs to a tree. If you could step outside the Milky Way and look at it from far away, you would see that it is not a random cloud of stars. It has a shape, and that shape is the result of gravity acting over long spans of time. The central region is thicker and brighter, forming what astronomers call a bulge. Around that bulge stretches a wide, flattened disk where most of the stars, gas, and dust are found. From that disk extend spiral features, patterns where matter is more concentrated, slowly curving around the center. Surrounding all of this is a more diffuse halo of older stars and unseen mass that reaches much farther out than the bright parts alone. This structure is not perfectly sharp or rigid. The spiral arms are not fixed solid bands, but regions where stars and gas spend more time as they orbit, creating areas of slightly higher density. Matter moves in and out of these regions, much as cars on a ring road may cluster in slower moving sections without forming a permanent wall. The spiral pattern is something that emerges from the motions of many individual objects under the influence of gravity, not something imposed from outside. It appears orderly because the same physical rules apply everywhere within the galaxy. The disk itself is relatively thin compared to its width. Most stars lie within a limited distance above and below a central plane. When we look along this plane from our position inside it, we see the dense concentration of stars that creates the bright band of the Milky Way in the sky. When we look away from the plane, toward the regions above or below the disk, the number of stars in that direction decreases, and the sky appears darker. The thickness of the disk is therefore not just a geometric property, it shapes what we see and how we understand our surroundings. Near the center, the bulge adds another layer to the picture. In that region, stars follow more tightly bound orbits in many directions, creating a rounded, brighter structure that rises above the plane of the disk. The stellar population there is different in age and distribution from the stars in the outer disk. Gas clouds and dust are more abundant in some central regions and sparser in others. Observation in visible light is limited by the dust that obscures our line of sight, but other wavelengths reveal the underlying structure. Infrared and radio observations show the arrangement of stars and gas, confirming that the bulge is a real, three-dimensional feature, not an illusion. Beyond the visible disk and bulge lies the halo. It contains individual stars and clusters that orbit the galaxy in large, extended paths. The halo stretches far beyond the main luminous regions of the Milky Way, blending gradually into the space between galaxies. It is faint and difficult to see directly, but its presence is inferred from the motion of stars and from the way the galaxy's gravity acts on its surroundings. The halo also contains much of the dark matter that gives the Milky Way its overall mass, shaping the orbits of stars in the disk and helping to hold the spiral structure together. Thinking of the Milky Way in terms of these components can bring a sense of order to something that might otherwise feel impossibly large. There is the central bulge, dense and bright, the wide disk with its spiral arms, the more diffuse halo extending outward, and the unseen dark matter woven through it all. Each part has its own typical kinds of stars, its own mix of gas and dust, and its own characteristic motions, yet all of them are part of a single system. The structure is not perfectly symmetrical and not fixed in time, but it is coherent. It holds together in a way that can be described, measured, and understood. From our location in the disk, we do not see this full shape directly. We reconstruct it from many separate lines of evidence. Still, even without an external view, it is possible to form a calm mental picture. A central swelling of stars, a flattened spinning disk, curved patterns where matter is slightly more concentrated, and a quiet, extended halo around it all. Within that layered structure, the Sun and Earth follow their steady paths. The shape of the Milky Way is not a decoration added to the universe. It is the natural arrangement of matter under gravity at this scale, a stable framework that has been in place for a very long time and will remain in place while individual stars and worlds live out their shorter histories within it. When astronomers describe the Milky Way, they often say it contains hundreds of billions of stars. This is a large phrase, and it can feel distant from daily experience, but it is not meant to impress or overwhelm. It is simply the best estimate that careful observation and calculation can provide. The number is not known exactly, and it does not need to be exact. What matters is the sense that our galaxy is not made of a handful of stars scattered through space, but of a vast population, spread throughout the disk, bulge, and halo, all held together by gravity. Estimating how many stars a galaxy contains begins with smaller, more manageable regions. Astronomers observe patches of the sky where the Milky Way is visible, and count how many stars are detected at different brightness levels. They correct for the limits of their instruments, knowing that many stars will be too faint to see directly. They then combine these local counts with models of how stars are distributed through the disk. The process is similar to estimating the number of trees in a forest by sampling a few areas carefully and extending the results, always with an awareness of uncertainty. Not all stars are the same, and this variety must be taken into account. Some stars are much more massive and luminous than the Sun. They shine brightly but live for shorter periods. Others are smaller and cooler, releasing less light but lasting far longer. There are also stars that have left the main stage of their lives, fading, swelling, or cooling as they move into later phases of their evolution. When astronomers build models of the Milky Way, they include a mix of these different types, weighted by how common each one is believed to be. From our location inside the galaxy, most of these stars are invisible to the unaided eye. Even with a telescope, only a fraction of the total population can be resolved individually. Many stars are too far away, too faint, or hidden behind dust clouds, yet their combined presence is still felt. The light they contribute shapes the overall glow of the Milky Way in the sky. Their gravity influences the motion of gas, dust, and other stars, helping to define the structure of the disk and the spiral patterns that move through it. The idea of hundreds of billions of stars can feel abstract, but it can also be approached gently. Instead of trying to picture them all at once, you can imagine that wherever you look within the Milky Way, if you could move closer, new stars would always come into view. In one direction, you might find a dense cluster where stars form together from the same gas cloud. In another, a more open region with older stars spread apart. In yet another, a patch of gas that is slowly cooling and fragmenting, preparing to form new stars in the distant future. The richness lies not in a single scene, but in the knowledge that such scenes exist in great number. Among this population, the Sun is an ordinary star. It is not the largest, brightest, or most massive. It belongs to a common class that contributes steadily to the light and energy of the galaxy without drawing special attention. This ordinariness is not a limitation. It is part of what allows solar systems like ours to form and remain stable over long periods. In a galaxy crowded with extreme objects, a star like the Sun provides a quiet environment where planets can orbit, cool, and develop their own histories. Thinking of the Milky Way as a system of countless stars can bring a sense of continuity. Each star is born, lives for a time that may be long or short, and eventually changes into another form. Material is returned to the surrounding space, where it can be incorporated into new generations of stars and planets. Over galactic timescales, this cycle repeats across many regions of the disk. The number of stars at any given moment reflects this ongoing balance between formation and loss, a balance that has been maintained for a very long time. As you rest, you do not need to hold the full number in mind or imagine every star. It is enough to know that the Milky Way is not a sparsely populated place. It is filled with stars of many kinds, most of them too distant to see, all of them moving within the same gravitational field. The light that reaches Earth is only a small sample of what exists, yet even that small sample is enough to trace the outline of the galaxy in the sky. The rest remains in the background, steady and unhurried, part of a larger structure that continues whether you think about it or not. Inside the Milky Way, stars are not fixed decorations. They are objects with full life cycles, unfolding over timescales far beyond human experience. Each star begins as part of a cold, diffuse cloud of gas and dust. In most regions, this material remains spread out and quiet, but in some places it slowly gathers under its own weight. Gravity pulls the particles closer together, increasing the density and temperature of the cloud. Over long periods, parts of the cloud contract into smaller, denser fragments. As a fragment continues to collapse, the material at its center grows hotter and more compressed. At a certain point, the conditions become extreme enough for nuclear fusion to begin. Hydrogen nuclei start to combine into helium, releasing energy. When this happens, the object stops collapsing and settles into balance. The outward pressure from the fusion reactions matches the inward pull of gravity. A new star has formed, shining steadily as long as this balance is maintained. The properties of a star are set mainly by its mass. A star that forms from a larger fragment of gas becomes more massive and hotter. It releases energy at a higher rate and appears brighter and bluer. A less massive star shines more gently and uses its fuel more slowly. The Milky Way contains many more low-mass stars than high-mass ones. These small stars can live for timescales that extend far beyond the current age of the universe, burning quietly without ever becoming especially bright. The Sun is a medium-mass star. It has been fusing hydrogen in its core for billions of years, and will continue to do so for billions of years more. During this long, stable phase, its size and brightness change only gradually. Many stars in the Milky Way are in a similar state, spending the majority of their lives on what astronomers call the main sequence. In this phase, the star's behavior is predictable. Its structure remains in approximate balance, and it radiates energy at a fairly steady rate. Eventually, the available hydrogen in the core of a star becomes sufficiently depleted that fusion there can no longer proceed in the same way. Gravity then begins to dominate again, and the core contracts. The outer layers respond by expanding and cooling. The star becomes larger and redder, entering a giant phase. For a star like the Sun, this is a slower transformation, not an instant event. The outer layers become more extended, and the star loses matter into the surrounding space. For very massive stars, later stages are more complex and more rapid. Their cores can reach conditions where heavier elements are formed through fusion, building up layers of different materials. These stars use their fuel at a much higher rate and pass through their life cycle in a fraction of the time taken by smaller stars. When their cores can no longer support further fusion, the balance fails. The result is a collapse of the core and a violent release of energy that can briefly outshine an entire galaxy. Despite the intense energy involved in these final stages, the long-term outcome is still consistent with the slow, ordered behavior of the galaxy as a whole. The outer layers of dying stars enrich the surrounding gas with heavier elements, including those that later become part of new stars, planets, and solid bodies. The cores may remain as dense remnants, such as white dwarfs, neutron stars, or black holes, each with its own stable form under extreme conditions. Across the Milky Way, these processes occur in many places at once, but always over extended periods. Star-forming regions emerge where gas clouds become dense enough. Older stars approach the end of their lives and return material to the interstellar medium. New stars form from that enriched material. The details differ from one region to another, yet the overall pattern remains the same. Birth, long stability, and eventual change all happen within the larger framework of the galaxy's structure and gravity. From the perspective of a single human life, stars may appear unchanging. Their positions shift only slowly, their brightness seems constant, and their colors do not noticeably alter. The life cycle described here is inferred not from watching one star from beginning to end, but from observing many stars at different stages and understanding how they fit into a continuous sequence. In this way, the Milky Way reveals itself not only as a collection of stars, but as a place where those stars are continually forming, evolving, and returning material to the space between them, in a quiet, ongoing cycle. When people imagine the Milky Way, they often picture only stars, bright points scattered through darkness. In reality, much of the galaxy consists of the space between those stars. This space is not completely empty. It is filled with a very thin mixture of gas and tiny dust particles, collectively known as the interstellar medium. The density of this material is extremely low compared to air on Earth, but because it fills enormous volumes, it plays a central role in how the galaxy functions and evolves over time. The gas in the interstellar medium is made mostly of hydrogen, the simplest and most common element in the universe. There is also helium and trace amounts of heavier elements. Under typical conditions in the Milky Way, the atoms and molecules of this gas are separated by large distances. In many regions, the average separation between particles is greater than the width of a small room. Yet on the scale of a galaxy, even such sparse material adds up. It collects into clouds of many different sizes, shapes, and densities, forming a kind of invisible structure within the visible structure traced by the stars. Dust in the interstellar medium is not like dust in a house. It consists of microscopic solid grains, often made of silicates, carbon compounds, or icy coatings. These grains are much smaller than the width of a human hair. They interact with light by absorbing and scattering it, which is why some regions of the Milky Way appear darker when viewed in visible light. The dust does not form thick layers in space. Instead, it is mixed with the gas in low concentrations. Over long distances, even this thin distribution can block or dim the light from background stars. The interstellar medium is not uniform. Some regions are warm and more diffuse, with gas spread thinly and dust scattered loosely. Other regions are colder and denser, where material has gathered into clouds. The coldest and densest clouds can become sites of future star formation. Inside them, gas and dust can cool effectively, allowing gravity to contract parts of the cloud into denser structures. Over long periods, those structures may become the birthplaces of new stars and planetary systems. In this way, the interstellar medium acts as a reservoir from which the next generation of stars is drawn. There are also regions where the gas is ionized, meaning that atoms have lost some of their electrons. This happens near hot, young stars that emit strong ultraviolet radiation. Their light strips electrons from nearby atoms, creating glowing clouds that can be observed in certain colors of visible and ultraviolet light. These regions trace areas where recent star formation has occurred. They are not permanent features. As the stars age and their radiation output changes, the gas cools and recombines, gradually returning to a more neutral state. Within the interstellar medium, there are also magnetic fields and streams of energetic particles known as cosmic rays. These components are not directly visible to the eye, but they influence how gas and dust move and interact. Magnetic fields can guide the motion of charged particles and gently shape the structure of clouds. Cosmic rays help determine the temperature and ionization state of the gas in some regions. Together, these factors contribute to a complex, dynamic environment that is still governed by simple physical laws. From the surface of Earth, The effects of the interstellar medium are most easily noticed in the dark bands that cut across the bright strip of the Milky Way. These are not gaps where stars are missing. They are places where dust in the foreground absorbs and scatters light from stars behind it, creating the appearance of lanes and patches. In other directions, the dust is less concentrated, and the combined light of background stars shines through more easily. The patterns we see are therefore shaped by the distribution of gas and dust along our line of sight. Over time, the interstellar medium is continuously recycled. Dying stars return material to space through winds and explosions, enriching the gas with heavier elements that were formed in their interiors. This processed material mixes with existing gas, cools, and eventually becomes part of new clouds. In those clouds, new stars and planets form, incorporating elements that once belonged to older generations of stars. The Milky Way is not only a collection of stars moving in orbits, but also a system in which matter flows slowly between stars and space, passing through different phases without ever leaving the galaxy as a whole. Thinking of the interstellar medium in this way can make the word between feel less like an empty pause and more like an active background. The space between stars is where the next stars will come from. It is where light is filtered, softened, and reshaped before reaching us. It is where magnetic fields, particles, and gas interact over long timescales, gradually preparing the conditions for future structure. Even in its thinnest, quietest regions, this medium is part of the Milky Way's ongoing life, linking individual stars into a larger, continuous system. When we look into the night sky from Earth, we cannot see the true center of the Milky Way with our eyes alone. In the direction of the constellation Sagittarius, there lies a region where the light of countless stars, clouds of gas, and thick lanes of dust overlap along our line of sight. The dust absorbs and scatters visible light so effectively that the innermost part of the galaxy remains hidden in ordinary observations. What we see from the ground is a dense, bright region crossed by darker streaks, but the core itself is veiled. Astronomers reach beyond this limitation by using forms of light that can pass through dust more easily. Infrared observations reveal stars that are invisible in ordinary photographs, laying out the crowded inner bulge of the Milky Way. Radio waves travel even more freely through dusty regions and can trace the motion of gas and the presence of energetic processes near the center. Together, these methods replace the blocked view in visible light with a clearer, though still indirect, picture of what lies at the heart of our galaxy. The environment in the galactic center is different from the quieter region where the sun resides. There, stars are packed much more closely together. The distances between them are far smaller than in our local neighborhood. Many of these central stars are massive and relatively young, formed from dense gas clouds that accumulated and collapsed near the core. Others are older, long-lived stars that have orbited the center for a very long time. The result is a complex mixture of stellar ages and types, all confined to a compact volume. Gas in the central region follows the influence of gravity and the motions of the stars. It forms streams, rings, and clouds that orbit and interact in ways that are more dynamic than in the outer disk. Shock waves, radiation from hot stars, and gravitational forces all shape this gas, compressing it in some locations and dispersing it in others. Dense pockets of gas can give rise to new stars, while surrounding radiation and winds from existing stars can erode or heat nearby material. Even so, these processes are guided by the same physical laws that govern the rest of the galaxy. One consequence of this concentration of mass is that stars in the center move at high speeds along tightly curved orbits. By carefully tracking the positions of certain stars over many years with precise instruments, astronomers can map these motions and use them to infer how much mass resides within their paths. The rapid changes in their trajectories show that a great deal of mass is confined to a relatively small region at the very center, far more than can be accounted for by visible stars alone. The bulge around the center is not a smooth sphere. It has structure and asymmetries that reveal a history of gradual evolution. Some measurements suggest that the central bulge has a slightly elongated form, more like a thickened bar than a perfect rounded cluster. This shape is thought to result from the slow rearrangement of stars in the inner disk over time, as their orbits respond to gravitational patterns in the galaxy. Such rearrangements happen over long periods, with individual stars simply following their own paths under the combined pull of the entire system. Although conditions in the galactic center are more intense, the scale involved means that individual events remain localized. Energetic phenomena, such as strong winds from clusters of massive stars, affect their immediate surroundings, but do not disrupt the entire galaxy. The influence of the core is felt primarily through its gravitational pull, which helps set the overall rotation pattern of the Milky Way. In that sense, the center functions as a deep anchor for the orbits of stars and gas throughout the disk. Compared with our position, the inner region of the galaxy is noisy in radiation and crowded in matter, but it is still a place of order rather than chaos. Orbits are stable, even if they are fast and compact. Stars rise and fade, gas flows inward and outward, and clusters form and disperse. Over long timescales, the combined effect of these processes shapes the distribution of mass, yet the center remains a persistent feature, defined by the concentration of matter and the gravity that follows from it. From the vantage point of Earth, the galactic center is both distant and constant. It does not change its position in the sky in any sudden way. It follows the same daily and yearly patterns as the rest of the stars, rising and setting as Earth rotates and orbits the Sun. Even when clouds, daylight, or bright city lights conceal it from view, the core of the Milky Way continues to act as the hidden heart of the galaxy, holding together the motions of stars and gas with its enduring gravitational presence. At the very center of the Milky Way there is an object that cannot be seen directly, yet its influence is clear. In that small central region, gravity is so strong that once light crosses a certain boundary, it cannot escape. This object is known as a supermassive black hole. It does not shine like a star or glow like a cloud of gas. Instead, its presence is revealed by the way it affects the motion and energy of the matter around it, especially the stars that move in close orbits near the galactic core. For many years, the idea of such a black hole in the Milky Way was based on indirect signs. Gas near the center was observed to move at high speeds. Emission from the region indicated a deep gravitational well. The most decisive evidence came from patient observations of individual stars close to the core. Astronomers measured their positions over many years and found that some of them followed tight, sharply curved paths around an unseen point. The mass required to hold these stars on their orbits is enormous, yet it must be confined to a volume smaller than the paths they trace. No cluster of normal stars or compact remnants can satisfy both conditions at once. The simplest and most consistent explanation is a single, very massive black hole. The word black hole often suggests something unusually dangerous, but the central object in our galaxy is simply another part of the overall structure. Its mass is millions of times that of the Sun, yet it is far away from us, buried deep in the inner region of the Milky Way. At the distance of the Sun, the black hole behaves like a concentrated point of mass within the larger gravitational field of the galaxy. It does not pull on us in a special or urgent way. Stars in the disk, including our own, follow their broad orbits around the galactic center, influenced by the combined mass of stars, gas, and dark matter spread throughout the disk and halo. Closer to the black hole, conditions change. Gas and dust that drift inward do not fall straight in. They tend to form a rotating structure around the central mass. As this material orbits, friction and compression heat it, and it emits radiation in many forms of light, including higher energy bands that do not reach the ground easily, but can be detected by instruments above Earth's atmosphere. In some galaxies, such infalling matter is abundant, and the central region shines so strongly that it outshines all the surrounding stars. In those cases, the galaxy is said to have an active nucleus. In the Milky Way, the central black hole is quiet by comparison. It shows modest activity, indicating that it is not currently receiving large amounts of gas. There may have been periods in the distant past when it was more active, and there may be such periods again in the future if new material moves inward. But on the scale of a human life, it behaves in a steady and undramatic way. From our position, its presence is important for understanding the galaxy, not for daily experience. Because no light can escape from inside the black hole itself, its boundary is not seen directly. Astronomers infer its size from theory and from the behavior of nearby matter. The region from which light cannot escape is called the event horizon. For the Milky Way's central black hole, this horizon is tiny compared with the orbits of the stars used to detect it. The details of what happens inside that boundary are described by the mathematics of gravity, but they remain beyond direct observation. In practical terms, it is enough to know that the black hole marks a small region where mass is concentrated extremely strongly. Even though a supermassive black hole is an extreme object, it fits naturally into the larger pattern of the galaxy. Its gravity helps shape the motions of stars in the central bulge and contributes to the overall binding of the inner regions. Its past activity may have heated or pushed gas, influencing where stars form near the core. At the same time, most of the Milky Way lies far outside its immediate reach and follows paths set by the total mass of the galaxy, not by the black hole alone. Thinking about this central object does not require imagining anything violent or urgent. You can picture it as a compact, heavy point at the center of a much larger, slower system, quietly fulfilling its role while stars and gas move in orderly orbits around it. The galaxy does not revolve around the black hole in isolation. Instead, the entire Milky Way, from the hidden core to the faint outer halo, responds to the combined pull of all its matter. Within that shared field, the central black hole is one important but contained feature, a reminder that even in the deepest part of the galactic center, the same calm physical laws hold that shape the space around the Sun and the quieter regions where we live. The Milky Way is not a fixed picture on the sky. It is a system in motion, and that motion is one of the ways we know it is bound together by gravity. Every star in the galaxy, including the Sun, follows a path around the center. Gas clouds, clusters, and even the diffuse halo all participate in this rotation. From our point of view on Earth, these motions are far too slow to notice directly. The patterns of the constellations change only very gradually over many lifetimes. Yet when measured carefully over long periods, the motion becomes clear. The Milky Way is turning. To describe this rotation, astronomers often speak of orbits. An orbit is the path one object takes around another under the influence of gravity. In the case of the Milky Way, there is not a single central object that carries all the mass. Instead, the mass is spread throughout the disk, bulge, and halo. A star at a particular distance from the center feels the combined pull of all the matter inside its orbit. The result is a smooth, curved path around the galactic core. For the Sun, this path is nearly circular and lies close to the plane of the disk. The time it takes for the Sun to complete one full orbit around the center of the Milky Way is immense. Estimates place it at several 100 million years. This span is sometimes called a galactic year. During one such orbit, continents shift on Earth, climate patterns change, and entire branches of life may appear or disappear. Human history occupies only a tiny fraction of a single galactic year. In practical terms, this means that for many generations, the Sun's position within the galaxy is effectively constant. The local arrangement of stars remains stable enough that the night sky preserves its familiar shapes. Not all stars move at the same speed. The rotation of the Milky Way follows a pattern that differs from the way planets orbit the Sun. In the solar system, planets farther from the Sun move more slowly. In the galaxy, stars at different distances from the center often move at roughly similar orbital speeds. This behavior is one of the clues that most of the Milky Way's mass is not in the form of visible stars or gas alone. The gravity needed to maintain this rotation suggests a large amount of additional, unseen matter spread through the halo. Despite these differences in speed, the overall motion is orderly. Stars do not cross one another's paths in sudden ways. Their orbits may be slightly elliptical, tilted, or perturbed by distant encounters, but the general pattern holds. Each star moves in response to the combined gravitational field, and the field itself changes only slowly as stars form, age, and move. Over very long periods, individual orbits can shift in shape or orientation, yet the disk as a whole continues to rotate as a coherent structure. Gas in the Milky Way also follows the rotation, though its behavior is influenced by pressure, temperature, and magnetic fields as well as gravity. In the disk, gas can collect into spiral patterns, where it is slightly compressed. These regions are often sites of ongoing star formation. As gas flows through a spiral feature, it can slow and then move on, much like cars moving through a region of heavier traffic. The spiral pattern remains in place even as individual stars and clouds pass through it, giving the galaxy its characteristic appearance without requiring each component to stay in a fixed arm forever. From our position inside the disk, we do not see this rotation as a sweeping motion across the sky. Instead, we infer it from careful measurements of the velocities of stars and gas in different directions. Spectroscopic observations reveal small shifts in the wavelengths of light caused by motion along our line of sight. By mapping these shifts across the sky, astronomers can build a picture of how the Milky Way turns. The result is a consistent view of a galaxy in slow, continuous rotation, with stars and gas moving in broad, overlapping circuits around the unseen core. For daily life, this motion does not produce any sensation. There is no feeling of turning or sliding as the sun moves along its galactic path. The distances involved are so great and the timescales so long that the movement is gentle and steady. Earth, the sun, and the surrounding stars share this motion together. In the same way that passengers in a smoothly moving train feel at rest relative to one another, we and the nearby stars are carried along by the rotation of the Milky Way without noticing it directly. It can be reassuring to think of this galactic rotation as a very slow background rhythm. While shorter cycles, such as days, seasons, and even historical eras, come and go, the larger motion continues in a calm, predictable way. The Sun has already completed many orbits since its formation, and it will complete many more. Throughout these long circuits, the Milky Way maintains its overall shape and coherence, holding stars, gas, and dust in a shared gravitational pattern that changes only gradually as time passes. Human time is measured in small, familiar units. Seconds, minutes, hours, days, and years organize daily life into steps that can be felt and remembered. A year is long enough to contain seasons, routines, and changes, yet short enough to fit into a clear mental picture. Even centuries, when considered carefully, still relate to people, events, and written history. When we turn to the Milky Way, those scales become only a thin surface on a much deeper stretch of time. The processes that shape the galaxy unfold so slowly that ordinary measures are not enough to capture them in a single thought. The age of the Milky Way is estimated to be comparable to the age of the universe itself, which is on the order of many billions of years. Its oldest stars formed when the universe was still young, and some of those stars are still present in the galactic halo. The disk where the Sun resides developed later, as gas settled and began to rotate in a more organized way. Over these long spans, stars have formed, lived, and ended their lives in many cycles. Each individual star has a finite duration, but the galaxy as a whole persists, renewing itself through the continuous flow of matter between stars and the space around them. The life of a star like the Sun extends across billions of years. During this time, it spends the vast majority of its existence in a stable phase, quietly fusing hydrogen into helium in its core. The slow changes in brightness and size over this interval are so gradual that they are not noticeable on human timescales. The Sun has already been active for several billions of years and is expected to continue in a similar state for several billions more. In the context of the Milky Way, this is a single, steady episode within the galaxy's long history. The orbit of the Sun around the galactic center adds another layer of time. A single circuit takes hundreds of millions of years. Since its formation, the Sun has completed multiple orbits, passing through different parts of the disk, encountering regions with slightly different densities of gas and stars. Each orbit overlaps with the life cycles of countless other stars, which themselves are at various stages of birth, maturity, and decline. At any given moment, the Milky Way contains stars in all these stages, spread throughout its structure, each following its own timeline. When we compare these scales to human life, the contrast is large, but it does not need to be unsettling. Instead, It can be seen as a way to stretch the sense of time gently. A single day is a small fraction of a human lifetime. A human lifetime is a small fraction of recorded history. Recorded history is a small fraction of the time since complex life arose on Earth. The age of life on Earth is a small fraction of the time the Milky Way has existed. Each step is longer than the one before it, yet the sequence is continuous. There is no break or jump, only an extension of the same axis of time into larger ranges. From the perspective of the galaxy, human events begin and end quickly. Civilizations rise and fall, technologies appear and spread, and ideas are created and forgotten, all while the sun advances only a small distance along its orbit. The positions of the bright stars in familiar constellations shift only slightly over the full span of recorded human history. This does not diminish the meaning of human lives. It simply places them within a wider context in which change is present but slow. The Milky Way provides a background of long-term stability against which shorter experiences unfold. As you listen, you do not need to hold every scale of time in focus. It is enough to know that the galaxy changes, but does so at a pace that is gentle compared to the rhythms of daily life. Processes that take millions or billions of years do not demand immediate attention. They continue quietly whether you think about them or not. If your thoughts begin to slow, or if you notice your breathing becoming more regular, you can allow these larger spans of time to drift into the background. The Milky Way has been in motion for far longer than any single life, and will remain in motion long after this moment has passed. In this way, the concept of galactic time can support rest rather than disturb it. Knowing that the structures around you evolve so slowly can make present concerns feel less urgent. The galaxy is not rushing. Its stars follow patient paths, its gas clouds change shape at a measured pace, and its overall form persists while smaller details shift within it. You are listening during a brief interval in this extended history, and it is entirely acceptable to let that interval narrow even further as you approach sleep. The Milky Way will continue its quiet rotation as you rest, holding its long chronology in place while your own sense of time softens and stretches. Around the bright disk and central bulge of the Milky Way stretches a more diffuse region known as the halo. This halo is not a sharp shell or a glowing envelope that you would notice in a simple picture. Instead, it is a vast, extended volume of space containing a sparse population of stars and star clusters, along with a large amount of unseen mass. It reaches far above and below the plane of the disk and far beyond the visible spiral structure. From Earth, we do not perceive the halo as a distinct feature in the sky. Its stars are scattered and faint, mixed among the many other points of light that fill the night. One of the most recognizable components of the halo is the set of objects known as globular clusters. These are dense, roughly spherical groups of stars, often containing hundreds of thousands of members bound together by gravity. The stars in globular clusters are typically old and low in heavier elements, which suggests that they formed early in the history of the galaxy. The clusters orbit the Milky Way on large, elongated paths that take them far above and below the disk. When observed through a telescope, they appear as compact swarms of light, gradually growing denser toward the center. The individual stars in the halo, outside of clusters, also tend to be older and poorer in heavy elements than the average stars in the disk. This difference in composition offers a clue to the sequence of events that built the Milky Way. Heavy elements are produced inside stars and released into space when stars lose mass or reach the ends of their lives. Over time, gas enriched with these elements participates in new rounds of star formation. Younger stars therefore contain more of these elements than older ones. The low heavy element content of halo stars indicates that they formed before much enrichment had occurred. Some of the stars and clusters in the halo may be remnants of smaller galaxies that were absorbed by the Milky Way in the distant past. As the galaxy grew through mergers and interactions, stars from those systems were captured and spread out along extended orbits. Their motions and compositions still carry traces of their origins. Astronomers study these properties to reconstruct how the Milky Way assembled itself over time, using the halo as a kind of archive in which earlier stages of growth are recorded. The halo also contains most of the galaxy's dark matter. This unseen mass does not emit or absorb light, but it reveals itself through gravity. The way stars and gas move in the outer parts of the Milky Way indicates that there is far more mass present than can be accounted for by visible matter alone. Models that include a broad, roughly spherical halo of dark matter provide a good match to these observations. This dark component extends beyond the luminous halo of stars and clusters, shaping the orbits of objects throughout the galaxy. Although the halo is extended and influential, it is extremely thin in terms of matter density. A spacecraft traveling through it would not encounter noticeable clouds or continuous structures. The stars are widely separated, and the dark matter is spread smoothly on large scales. Its presence is detected not by direct contact, but by careful measurement of motion, and by comparing what is seen with what would be expected if only visible matter were present. For daily experience on Earth, the halo has no direct effect that can be felt. Its gravity is part of the overall pull that binds the Milky Way, but its influence is spread gently over great distances. When you look up at the night sky, some of the faint, solitary stars belong to this halo population, moving on wide orbits that carry them far from the disk. They do not announce themselves as different, they are simply part of the larger field of light. Knowing about the halo adds depth to that field, showing that the galaxy extends far beyond the bright band of the Milky Way, with ancient stars and quiet mass forming a surrounding structure that has been in place for a very long time. When astronomers studied the rotation of the Milky Way in detail, they encountered a consistent pattern that could not be explained by visible matter alone. Stars and gas clouds in the outer parts of the galaxy were moving faster than expected. If only the mass of the stars, gas, and dust we can see were present, those outer objects should have been moving more slowly, or they would not remain in stable orbits. Instead, their speeds remained high over a wide range of distances from the center. This indicated that something else was contributing to the galaxy's total mass. To account for these observations, scientists introduced the concept of dark matter. Dark matter is not a new kind of light or a special form of gas. It is a name for matter that exerts gravity but does not emit, absorb, or reflect light in any way that current instruments can detect. Its presence is inferred from its gravitational effects. In the Milky Way, the simplest explanation for the measured rotation speeds is that a large amount of this unseen matter surrounds and permeates the visible galaxy, forming an extended halo that adds mass where no luminous material is observed. The idea of dark matter does not come from one measurement alone. It is supported by many lines of evidence from different galaxies and from larger structures in the universe. In spiral galaxies similar to the Milky Way, rotation curves, which show orbital speed as a function of distance from the center, often remain flat or nearly flat at large radii, instead of dropping off in the way they would if only visible matter were present. In clusters of galaxies, the motions of individual galaxies also suggest more mass than can be seen. Patterns in the cosmic microwave background, a faint radiation left over from the early universe, further support the presence of a large, non-luminous component. In the context of the Milky Way, dark matter is modeled as a roughly spherical halo that extends well beyond the visible disk and bulge. Within this halo, the density of dark matter is higher near the center and gradually decreases with distance, but it remains present out to radii where the visible galaxy tapers off. Stars, gas, and clusters move within this combined gravitational field. Their orbits are shaped not only by the mass we can see, but also by the dark matter halo that surrounds them. Despite the strong evidence for its gravitational influence, the exact nature of dark matter remains unknown. It is not made of ordinary atoms arranged in a way that simply hides them. Observations and theoretical work suggest it is composed of particles that interact only weakly with normal matter and with light. Many experiments aim to detect these particles directly or to observe their effects in controlled conditions, but so far no definitive detection has been made. In this sense, dark matter is both a practical tool in our models and an open question in physics. For the structure and stability of the Milky Way, dark matter is important because it provides the additional mass needed to keep stars in their observed orbits. Without it, the outer regions of the galaxy would not behave as they do. With it, The rotation pattern becomes a natural consequence of the total mass distribution. The visible stars, gas, and dust can be thought of as a luminous layer embedded within a more extended, invisible component. Together, these parts form the full gravitational framework of the galaxy. Although dark matter is a central topic in modern astrophysics, it does not change the calm, large-scale picture of the Milky Way. It does not introduce sudden forces or unpredictable effects in daily life. Its influence is steady, spread smoothly over large volumes of space, and present over the entire lifetime of the galaxy. When we speak of the Milky Way as a stable, rotating system, we are quietly including dark matter in that description, acknowledging that much of what holds the galaxy together cannot yet be seen, only measured through the motions of the objects we can observe. The Milky Way does not exist alone in space. Around it moves a collection of smaller galaxies, bound to it by gravity. These are known as satellite galaxies. They vary in size, shape, and brightness, but they share a common feature. Their paths are controlled by the gravitational field of the Milky Way. Some are close and relatively prominent, others are faint and difficult to detect. Together, they form a loose system of companions orbiting a larger central galaxy. Many of these satellites are dwarf galaxies. Compared to the Milky Way, they contain far fewer stars and much less gas. Some are irregular in shape, showing no clear spiral or elliptical structure. Others are more regular, forming small, rounded systems where stars are spread smoothly through a compact volume. Their reduced size does not make them unimportant. They contribute stars, gas, and dark matter to the environment of the Milky Way and record stages of its past growth. Over long timescales, interactions between the Milky Way and its satellites leave visible traces. As a smaller galaxy orbits, tidal forces from the larger galaxy can stretch it, pulling stars and gas into elongated streams. These streams can wrap partway around the Milky Way, forming faint arcs that can be detected with sensitive surveys. In some cases, the material from a disrupted satellite eventually blends into the halo of the larger galaxy, becoming part of its extended stellar population. By mapping these streams, astronomers can reconstruct past encounters and understand how the Milky Way has grown by accreting smaller systems. Some satellite galaxies still retain much of their original structure. They move on long, slow orbits that carry them around the Milky Way over many billions of years. Their stars often possess different chemical compositions than typical disk stars, reflecting their separate histories of star formation. When these satellites pass closer to the Milky Way, their gas can be disturbed or even removed, feeding the larger galaxy's reservoir of material. At other times, they continue along paths that keep them at a greater distance, evolving more quietly under their own internal gravity. The presence of satellite galaxies is a natural outcome of how structure forms in the universe. Matter does not collapse directly into a single large object. It first forms many smaller clumps that later merge and combine. Some of these clumps are fully absorbed, while others remain as distinct companions orbiting the larger system that has grown around them. The Milky Way's satellites are remnants of this process, surviving examples of smaller galaxies that have not yet been completely incorporated into the main body. From Earth, most of these satellites are not prominent features in the night sky. Some are visible only as faint patches of light under very dark conditions. Others cannot be seen at all without telescopes and sensitive cameras. Their orbits are so large and slow that their positions relative to the Milky Way change only gradually over many human lifetimes. They do not announce their motion in any obvious way. Instead, they form a quiet, extended family around the galaxy, their presence recognized through careful observation rather than direct impression. Knowing that the Milky Way has companions helps complete the picture of our galaxy as part of a larger structure. The disk, bulge, and halo describe its internal shape. The satellites show that it also belongs to a hierarchy of systems, with smaller galaxies moving around a larger one. These companions are held by the same gravity that binds the stars of the disk and the clusters of the halo. While they follow their own paths, they are part of the same overall arrangement, contributing to the mass, history, and slow evolution of the Milky Way as it moves through space. Galaxies are not isolated islands. They share space with other galaxies, and over long periods their paths can bring them close enough to feel one another's gravity strongly. The Milky Way is no exception. It has interacted with smaller galaxies in the past, and will continue to do so in the future. These encounters do not look like quick crashes. Instead, they unfold slowly, over hundreds of millions or even billions of years, as two extended systems pass through each other's gravitational fields and gradually reshape one another. When a smaller galaxy approaches the Milky Way, tidal forces begin to act on it. The side of the smaller galaxy closer to the Milky Way feels a slightly stronger pull than the far side. Over time, this difference stretches the smaller system, drawing out stars and gas into elongated streams. Some of this material may become unbound from the original galaxy and start to follow new orbits around the Milky Way. The process is gradual. Stars do not collide directly because the distances between them are so large, but their paths are slowly redirected by the combined gravity of both galaxies. In some cases, a small galaxy can be almost completely disrupted. Its stars spread into the halo of the Milky Way, adding to the population of old, widely distributed stars on extended orbits. Its gas can be stripped and incorporated into the Milky Way's own gas reservoir, where it may eventually take part in new episodes of star formation. The original satellite ceases to exist as a separate object, but its components remain present, folded into the larger structure of the main galaxy. Observations of stellar streams in the halo provide evidence of these past mergers, like faint traces of paths once taken. Encounters with more massive companions are rarer, and they also proceed in a measured way. When two large galaxies approach one another, their mutual gravity distorts their shapes. Tails and bridges of stars and gas can form, extending far into space. As they pass and recede, they may lose energy through complex interactions, causing them to return and approach again. Eventually, repeated passes can lead to a full merger, in which the two galaxies combine into a single, larger system with a new overall structure. This process reshapes the orbits of stars and redistributes gas, but it does so over such long times that there is no single moment when two neat systems suddenly become one. The future of the Milky Way includes such a large-scale encounter. Observations indicate that it and the nearby Andromeda galaxy are moving toward each other. Over billions of years, they are expected to interact and eventually merge. From the point of view of stars within these galaxies, this does not mean a sudden collapse or the frequent collision of individual suns. The spaces between stars remain wide, and most stars simply follow new, gently curved paths within the changing gravitational field. The final merged galaxy will have a different shape and internal arrangement, but the physical laws guiding its behavior will be the same. Within the timescale of human life, these interactions are effectively frozen. The positions of neighboring galaxies shift only slightly, and their shapes appear stable in telescopes. The knowledge that mergers and encounters occur is based on the study of many galaxies at different stages, combined with simulations that follow the motion of matter under gravity. For the Milky Way, collisions and mergers are part of a long history and a long future, processes that add stars, mix gas, and slowly adjust the galaxy's structure while preserving the calm, large-scale order that characterizes its present form. To think about the future of the Milky Way, it helps to remember how slowly change occurs on galactic scales. The structures we see today are the result of many billions of years of gradual evolution. The processes that will shape the next stages are the same ones that have been operating since the galaxy formed. Stars will continue to be born from cold gas clouds, will live through long, stable phases, and will eventually return material to the interstellar medium. Gas will keep flowing through the disk, joining new star-forming regions, or drifting into quieter zones. The overall pattern is one of continued activity, but at a measured pace. Over very long times, the supply of cold gas available to form new stars will slowly decrease. Some of the gas will be locked into long-lived, low-mass stars. Some will be heated and dispersed by radiation and stellar winds, taking longer to cool and condense again. As this happens, the rate of star formation in the Milky Way is expected to decline. The galaxy will not suddenly stop forming stars at a single moment. Instead, Each new generation will be smaller than the previous one, and the disk will gradually become dominated by older, longer-lived stars. The orbits of stars around the galactic center will also continue to evolve. Small perturbations from passing stars, spiral patterns in the disk, and the gravitational influence of the bar and bulge can slowly alter the shapes and orientations of these paths. Individual stars may move slightly inward or outward over billions of years, sampling different regions of the disk. Despite these adjustments, the overall rotation pattern will remain recognizable. The Milky Way will continue to turn as a coherent system, with stars and gas following paths set by the combined mass of visible and dark matter. Interactions with satellite galaxies will carry on as well. Some satellites will lose stars and gas to tidal forces, adding material to the halo and outer disk. Others may eventually merge more completely with the Milky Way, contributing their contents to the main body of the galaxy. Streams of stars from past mergers will become more mixed, their original structures fading into the background distribution of halo stars. Each such event leaves a subtle imprint in the motions and compositions of stars, but none changes the fundamental nature of the Milky Way as a large, gravitationally bound system. The anticipated encounter with the Andromeda Galaxy lies far in the future, on a timescale of several billions of years. As the two galaxies approach each other, their shapes will distort, and their stars will be redistributed into new patterns. Gas clouds may be compressed, triggering bursts of star formation in some regions. Over a series of passes, the two systems are expected to combine into a single, larger galaxy with a new overall structure, likely more rounded and less clearly disk-like than the Milky Way is now. From within, this transition would unfold slowly. Generations of stars and any planets they host would experience it as a long, drawn-out change in the larger background, not as a sudden event. On even longer timescales, beyond the merger, star formation in the combined galaxy will continue to decline as gas is used or dispersed. Existing stars will age. Many will end their lives as white dwarfs, neutron stars, or black holes, slowly cooling or remaining as compact remnants. The galaxy will shift from a place of active star birth to a system dominated by long-lived, faint objects. Yet throughout these stages, gravity will still bind the stars and remnants into a common structure. The motions will remain ordered, even if the bright spiral pattern of the present Milky Way has long since faded. Thinking about this future does not require imagining sharp endings. The galaxy does not have a single final moment. Its evolution consists of many small steps taken over intervals that far exceed the span of human or even planetary history. The Milky Way has already passed through many phases to reach its current state, and it will pass through many more, each one governed by the same simple physical laws. From the perspective of this larger timeline, the present moment is one stage among many, a quiet interval in a very long sequence, during which the galaxy continues its slow rotation and steady transformation. For much of human history, the Milky Way was not a diagram or a set of measurements. It was something seen directly in the night sky. When artificial light was rare, the pale band of the galaxy was a regular presence, returning on clear nights as a quiet feature overhead. People learned its appearance the way they learned the shapes of familiar landscapes. It did not need explanation to serve as a point of orientation. It was simply part of the world after dark, a steady signal that the sky was broad and ongoing beyond the reach of daily concerns. Even now, in places where the sky is still dark, the Milky Way can offer the same kind of calm. Looking up, the eye meets many individual stars, but the band of the galaxy lies across them like a gentle backdrop. It does not demand focus. It is easier to notice when attention is soft, when you are not searching for one particular object but allowing the whole field of light to come into view. The diffuse brightness, crossed by darker lanes, gives a sense of structure without sharp boundaries. It suggests that there is more continuity above than any single point of light can show. The presence of the Milky Way in the sky also shows how constant some aspects of the world are. Weather changes, clouds move, and the brightness of the moon waxes and wanes, but behind these shifting elements, the galaxy remains in place, slowly turning with the rotation of Earth. Over the course of a night, the band appears to tilt and slide as the planet spins. Over the course of the year, different sections of the galactic plane become visible as Earth moves around the Sun. These motions are regular and predictable. They repeat in patterns that extend far beyond one person's memory. Because the galaxy changes so slowly, it can serve as a reference when the mind is busy. The knowledge that the stars and the Milky Way have been present for countless generations and will remain present for many more offers a sense of scale. Immediate thoughts, tasks, and worries exist within a much larger, quieter setting. You do not need to ignore those thoughts. It is enough to recognize that they occupy only a small layer above a deeper continuity. The galaxy does not react to them. It turns at the same rate whether a day is crowded or calm. If you imagine yourself under a clear sky, even while you are indoors, you can picture the Milky Way as a soft arc above you. The details of its shape do not need to be sharp. It is sufficient to hold the idea of a broad, faint band, made of many distant stars, extending from one horizon to another. Around it, the rest of the sky is filled with individual points of light and dark spaces between them. Beneath it, Earth rotates steadily, carrying you with it. You are not separate from this motion. You are part of it simply by existing on the planet's surface. As your breathing becomes slower and more regular, you can let the image of the night sky grow less precise. The exact arrangement of stars does not matter. The important part is the sense of something stable and unhurried overhead, something that does not require action from you. The Milky Way continues to shine with the combined light of its many stars, whether you picture it clearly or not. You can allow your thoughts to drift, knowing that beyond the room you are in, beyond clouds and buildings and weather, the galaxy is present as a calm, continuous background. It will remain there while you rest, holding its place as a quiet signal of the larger order in which your own smaller timescales unfold. When we talk about the Milky Way, we are not only describing distances in space, we are also describing distances in time. The light that reaches Earth does not arrive the moment it leaves its source. It travels at a finite speed, crossing the space between stars over long intervals before it encounters an eye, a camera, or a telescope. Because of this, every view of the galaxy is a look into the past. The farther away a star or cloud of gas is, the further back in time we see it. Light moves extremely quickly compared with everyday motions, but the distances within the Milky Way are so large that even this high speed requires time. When we express distance in light years, we are directly linking space and time. 1 light year is the distance light travels in 1 year. If a star is 100 light years away, the light we see tonight left that star 100 years ago. For objects much farther out in the galaxy, the look-back time can reach tens of thousands of years. We are observing them as they were long before the present moment, even though their light is only arriving now. This delay does not distort the basic structure of the Milky Way. The galaxy changes too slowly for differences over these timescales to alter its overall appearance. A star seen at a distance of several thousand light years has moved a little since the light left, but not enough to break the pattern of the disk or the shape of a spiral arm. Gas clouds may have shifted, formed stars, or dispersed slightly, yet the large-scale arrangements remain recognizable. The view we construct of the galaxy is therefore a mosaic of scenes from different times that still fit together into a coherent picture. For astronomers, the finite speed of light is not an obstacle but a tool. It allows them to study how objects and systems behave at different stages of their evolution. Within the Milky Way, the range of look-back times is modest compared with the age of the galaxy, but it still provides useful information. By observing star clusters at different distances, scientists can compare younger and older populations. By mapping emission from gas in various regions, they can see where star formation has occurred more recently and where it has been quiet for longer intervals. The concept of light travel time also applies when we look beyond the Milky Way to other galaxies. There, the delays become much larger, reaching millions or billions of years. Distant galaxies are seen as they were when the universe itself was younger. In that wider context, the Milky Way is one point on a long continuum of cosmic history. Yet for this story, it is enough to remain within our own galaxy, where light travel time gently links our present to the more recent past, not to the distant beginning of the universe. On a personal level, thinking about light travel can shift the feeling of distance. The faint glow of the Milky Way in the sky is not a single moment of brightness. It is the sum of contributions from stars at many different distances, sending out light that has been traveling calmly through space for a long time. Some of the photons entering your eye from the band of the galaxy tonight began their journey before you were born. Others started out when human cultures were in very different stages. All of them have moved in straight lines through the quiet vacuum between stars, untouched until they finally meet an observer. You do not need to trace each path to appreciate this. It is enough to know that the light you see is a record of how the galaxy was distributed over a range of past times, assembled into a single view on the sky. The Milky Way does not flash or flicker as a whole. It presents a steady appearance because its changes are slow compared with the time it takes light to cross its width. As you picture the band of the galaxy, you can imagine that you are not only looking outward into space, but also slightly backward into time, receiving gentle signals from a long, continuous process that has been unfolding quietly for many thousands of years. To understand the Milky Way as more than a pale band in the sky, astronomers rely on instruments that extend far beyond the sensitivity of the human eye. For most of human history, observation meant looking carefully and remembering what was seen. Patterns were noted, positions of stars were tracked, and the paths of planets were recorded against the background of the constellations. These careful records laid the groundwork, but they could not reveal the full structure of the galaxy. The human eye collects only a small amount of light and does not distinguish very fine details. The invention of the telescope changed this. By gathering more light and focusing it, telescopes make faint objects visible and reveal structure where the unaided eye sees only smooth brightness. Simple telescopes showed that the Milky Way is made of countless individual stars, densely packed along the band. As instruments improved, astronomers could separate the glow into more and more components, studying clusters, clouds, and individual stars at different distances. Each improvement in optical quality and size added another layer of detail to the picture. Modern telescopes extend this reach even further. Some are placed on high mountains, where thinner air and less moisture reduce distortion. Others orbit above Earth's atmosphere, avoiding the blurring effects of air entirely. They collect light not only in the visible range, but also in radio, infrared, ultraviolet, and other parts of the spectrum. Each of these reveals different aspects of the Milky Way. Radio telescopes trace cold gas clouds that are invisible to the eye. Infrared instruments see through dusty regions to the stars embedded within them. X-ray and gamma-ray detectors catch the signatures of energetic processes near compact objects and hot gas. Measurements do not stop at images. Spectroscopy, the study of how light is spread into its component wavelengths, allows astronomers to determine the composition, temperature, and motion of stars and gas. When a star is moving toward or away from us, its spectral lines shift slightly to shorter or longer wavelengths. By measuring these shifts, scientists can infer the star's speed along the line of sight. Repeated across many regions of the sky, such measurements build up a map of how the Milky Way rotates and how its different parts move relative to one another. Distance is another key quantity. It is not enough to know how bright an object appears. To place it correctly within the galaxy, astronomers need to know how far away it is. Various methods are used for this, depending on distance and object type. For nearby stars, tiny shifts in position against more distant background stars, measured over the course of Earth's orbit, provide direct geometric distances. For more distant objects, standard candles, whose true brightness is known, help extend the scale. Combined, these techniques turn the sky from a flat pattern into a three-dimensional structure. All of these observations are assembled into models of the Milky Way. No single map captures the galaxy completely. Instead, many different surveys and measurements overlap, like layers of transparent sheets, each highlighting one aspect. One map shows gas density, another shows stellar distribution, another traces the motion of particular components. Computer simulations test whether a given arrangement of mass and motion remains stable over time. When models reproduce what is observed, confidence grows that they reflect the true underlying structure. From the perspective of someone on Earth, this work happens quietly in the background. Telescopes open their shutters night after night. Detectors collect photons that have traveled for thousands of years from distant parts of the galaxy. Data are stored, compared, and analyzed with patient methods that value consistency over speed. The Milky Way itself continues to rotate, unconcerned with the instruments pointed toward it. Little by little, the picture becomes clearer. The galaxy that once appeared as a simple band of light now emerges as a structured system, mapped not through a single image but through many measured pieces that fit together into a calm, coherent whole. The Milky Way can be observed in many kinds of light, not only in the narrow range that human eyes can see. What we call visible light is a small portion of the electromagnetic spectrum, a continuous range of waves that share the same physical nature but differ in wavelength and energy. On either side of the visible range lie other forms of light. At longer wavelengths, there are infrared and radio waves. At shorter wavelengths, there are ultraviolet, X-rays, and gamma rays. Each of these provides a different view of the galaxy, revealing features that are hidden or muted in ordinary photographs. In visible light, the Milky Way appears as a crowded field of stars and a diffuse band crossing the sky. Dust clouds carve out dark lanes where starlight is blocked. Bright regions mark zones where many stars are concentrated or where clusters are located. This view is familiar and useful, but it is incomplete. Dust in the interstellar medium absorbs and scatters visible light very effectively, especially light at shorter wavelengths. As a result, dense, dusty regions appear as silhouettes rather than transparent windows into their interiors. Infrared light penetrates dust more easily. When astronomers observe the Milky Way in infrared wavelengths, they see stars that are largely hidden in visible light, especially in the central bulge and in dense parts of the disk. Cool dust and gas that emit weakly in the visible range can glow more clearly in infrared. Star-forming regions become more apparent, as young stars still embedded in their birth clouds stand out against the background. This allows a more complete census of the stellar population and a better understanding of how matter is distributed near the galactic center and along the spiral features. Radio observations add another layer. Neutral hydrogen gas, which is abundant in the Milky Way, emits light at a specific radio wavelength when the orientation of the electron and proton in the atom changes relative to each other. This emission is very faint, but radio telescopes can detect it across large regions of the galaxy. By mapping this signal, astronomers trace where gas is located, how it moves, and how it is organized into arms, streams, and clouds. Because radio waves are not strongly affected by dust, they provide a way to see through the dusty disk and study the galaxy's structure, even in directions where visible light is heavily obscured. Different wavelengths also highlight different physical processes. Hot, young stars can be prominent in ultraviolet light. Very hot gas near compact objects, such as neutron stars or black holes, can emit X-rays. Energetic particles moving in magnetic fields can produce radio and X-ray emission. By comparing images made at several wavelengths, scientists can identify which regions are dominated by star formation, which contain older, cooler stars, and which are shaped by more extreme phenomena. No single band contains the whole story. The Milky Way is understood through the combination of all these views. From the perspective of someone on Earth, most of these forms of light cannot be seen directly. The atmosphere blocks some wavelengths and distorts others. Instruments are needed to collect and interpret them. Telescopes on the ground and in space convert invisible signals into images and measurements that can be studied. The result is a set of complementary maps, each one showing the same galaxy through a different window. When these maps are aligned and compared, the Milky Way appears not only as a band of stars, but as a layered system of gas, dust, radiation, and magnetic fields, all governed by the same underlying physics. Knowing that the galaxy can be viewed in many kinds of light does not require you to imagine each one in detail. It is enough to understand that the familiar visible band is only one expression of a richer structure. Behind the soft glow in the night sky lies a spectrum of signals, each carrying information about a different part of the Milky Way. Together, they turn a single pale arc into a more complete picture of a galaxy that is active, ordered, and varied, even when it appears to the eye as a simple strip of brightness across the darkness. From our position inside the Milky Way, we can never step outside and take a single photograph of the entire galaxy. Every view we have is from one small point within the disk. This limitation means that the structure of the Milky Way must be inferred rather than directly seen. Astronomers build maps by combining many separate measurements, each one offering a narrow glimpse until a broader picture begins to emerge. The process is careful and gradual, more like assembling a detailed chart from scattered landmarks than like looking at a finished image. Distances are one of the most important ingredients in these maps. A star's position on the sky tells us only its direction, not how far away it is. To place a star correctly within the galaxy, its distance must be measured. For nearby stars, this is done through parallax, the small apparent shift in position against more distant background stars as Earth moves along its orbit. By measuring this shift precisely, astronomers can determine how far away the star is using simple geometry. For more distant stars and clusters, other techniques are used, such as comparing their observed brightness to the brightness expected for their type. Velocities add another layer. Using spectroscopy, astronomers measure how the wavelengths of light from stars and gas clouds are shifted by motion along the line of sight. Light from an object moving away is stretched to longer wavelengths, while light from an object approaching is compressed to shorter ones. By mapping these shifts across the sky, scientists can determine how different parts of the Milky Way move. These velocity maps reveal patterns of rotation, streaming motions along spiral arms, and the presence of large-scale structures that are not obvious in images alone. Gas is traced in a similar way. Radio observations of neutral hydrogen and molecular gas show how this material is distributed and how it moves. Peaks in radio emission indicate denser regions, while the spread in velocities along a line of sight hints at the arrangement of gas clouds at various distances. By combining these data with models of the galaxy's rotation, astronomers can reconstruct the likely positions of gas structures in the disk. The result is a set of maps that show where gas is concentrated, where spiral arms are located, and how material flows through them. Star clusters provide additional anchor points. Because the stars in a cluster form together and are at roughly the same distance, their combined properties can be used to estimate that distance with fairly high confidence. Once the cluster's position and motion are known, it becomes a marker on the galactic map. Many clusters, spread through the disk and halo, create a network of reference points. From this network, the overall shape and scale of the Milky Way can be refined. All of these elements are brought together in models that represent the galaxy as a three-dimensional structure. The models are not perfect. They are updated as new data arrive and as measurement techniques improve. Gaps remain where observations are sparse or uncertain. Even so, the broad outlines are robust. There is a central bulge, a rotating disk with spiral structure, a surrounding halo of stars and dark matter, and satellite galaxies in extended orbits. The invisible aspects, such as dark matter and parts of the halo that cannot be seen directly, are included through their gravitational effects. From the outside, this mapping work would not be necessary. A distant observer could simply look at the Milky Way and see its shape. From the inside, the situation is different. Every piece of the picture must be earned through measurement. Over many years, astronomers have built maps that transform the night sky from a flat dome into a volume filled with stars, gas, and clusters, each with a position and a path. The process turns what began as a glowing band into a charted system, where even the invisible components can be located and described with quiet confidence. The sun's path through the Milky Way is a long, quiet journey. It does not rush, change direction sharply, or weave unpredictably between other stars. Instead, it follows a broad, nearly circular orbit around the galactic center, embedded in the disk, along with many other stars that share a similar motion. This orbit is set by the combined gravity of the matter in the Milky Way, stars, gas, dust, and dark matter together. The result is a smooth path that carries the sun around the galaxy over hundreds of millions of years. In addition to this main orbit, the sun moves in smaller ways relative to the midplane of the disk. It does not sit exactly at the central layer where stellar density is highest, but oscillates gently above and below it. This motion is sometimes described as a slow bobbing, driven by the gravitational pull of the disk itself. As the Sun moves upward, gravity pulls it back toward the plane. As it passes through the plane, its momentum carries it to the other side, before gravity slows and reverses its motion again. These vertical oscillations take tens of millions of years to complete and are small compared with the overall galactic orbit. Along its path, the Sun passes through regions with slightly different densities of gas and stars. Some zones contain more interstellar material, others less. There may be times when the Sun is closer to a spiral feature and times when it is farther from such patterns. From the perspective of life on Earth, these changes happen very slowly. Entire geological eras unfold while the Sun advances through only a modest part of its orbit. The large-scale environment evolves, but on timescales far beyond those that shape human history or daily experience. The stars that appear near the Sun in the night sky are companions only in a loose sense. They are not bound to the Sun as planets are, but they move through the galaxy with their own orbits, some similar to the Sun's and some quite different. Over long periods, the set of stars that form our stellar neighborhood changes. Certain stars move closer, others drift away. Constellations that seem fixed from year to year gradually distort over millions of years. Yet these changes are too slow to notice within a human lifetime, so the familiar patterns on the sky remain essentially constant. As the Sun travels, it carries the solar system with it. Earth, the other planets, and smaller bodies all orbit the Sun, and together they are transported along the galactic path. There is no sensation associated with this motion. Just as passengers on a smoothly moving ship feel at rest relative to the deck and to one another, the inhabitants of Earth feel stationary relative to their immediate surroundings while the entire system moves through the Milky Way. The quiet regularity of the Sun's orbit provides a stable backdrop for the shorter cycles of days, seasons, and climatic shifts that occur on the planet itself. The Sun's journey is not unique. Many stars in the galactic disk follow similar orbits, each with its own slight differences in distance from the center, speed, and vertical motion. Together, they form the rotating structure of the disk. Over time, mutual gravitational influences, spiral features, and encounters with passing clouds can nudge these orbits gently, causing stars to move inward or outward by small amounts. These adjustments are gradual, the overall rotation persists, and the disk remains a coherent component of the galaxy. Thinking of the Sun's motion in this way places familiar surroundings in a wider context. The sky above, the patterns of stars, and the path of the Sun across the day are all part of a much larger, slower movement around the center of the Milky Way. There is no destination to reach and no point at which the journey begins or ends in any sudden way. The orbit is one element of the ongoing structure of the galaxy, a smooth, repeating path that continues as individual stars, planets, and lives follow their own shorter cycles within it. When we think about the Milky Way, it is natural to ask whether it is stable or changing. The answer is that it is both. On the one hand, the overall structure of the galaxy remains recognizable over very long periods. There is a central bulge, a rotating disk, spiral features, a surrounding halo, and a quiet population of satellite galaxies. On the other hand, every part of this structure is made of objects that move, evolve, and interact. Stars form and age, gas flows and changes state, and orbits shift gently over time. Stability in this context does not mean stillness. It means that change occurs in an ordered way, guided by consistent physical laws. At the level of individual stars, change can be significant. A massive star may live a relatively short life and end in a rapid, energetic event. A lower mass star may shine gently for billions of years and then cool as a compact remnant. Gas clouds can collect, fragment, and give rise to new stars, or they can be dispersed by radiation and winds. None of these processes breaks the galaxy. They are parts of its ongoing evolution. The material involved remains within the Milky Way, moving from one form to another, but always bound by the same gravitational field. On larger scales, patterns such as spiral arms and bars in the disk also evolve. These features are not rigid structures. They are regions where stars and gas spend more time, where density is slightly enhanced, and where star formation can be more active. Over time, the exact shape and strength of these patterns may change as orbits respond to the combined gravity of many components. The disk can thicken, the bar can grow or weaken, and the distribution of gas can shift. Yet throughout these changes, the galaxy remains a coherent, rotating system. The transitions are gradual, stretching over periods that far exceed human timescales. The presence of dark matter and the extended halo contributes to this stability. The halo provides a broad, smooth gravitational background that helps hold the disk and bulge together. It does not eliminate change, but it moderates it, supporting long-lived orbits for stars and clusters. Mergers with small satellite galaxies introduce new material and can rearrange stars in the halo, yet these events are spaced widely in time. Each one leaves evidence in the motions of stars, but the Milky Way does not lose its identity as a single galaxy. From the viewpoint of life on Earth, this combination of stability and change is important. The slow, predictable motion of the Sun around the galactic center and the long-term balance of forces in the disk provide a quiet background for the much faster processes that affect climates, ecosystems, and human societies. The galaxy does not impose sudden large-scale shifts on these timescales. Its changes are so extended that they form a nearly constant environment within which shorter cycles unfold. As you rest, this picture of the Milky Way can offer a sense of reassurance. The galaxy around you is not frozen, yet it is not in turmoil. It changes steadily and slowly, keeping its overall form while details shift within it. Your own thoughts and experiences occupy a much smaller window of time, moving more quickly against this calm backdrop. You do not need to follow every process or remember every star. It is enough to know that you are in a place where large structures hold together, where motion is orderly, and where the pace of change is gentle compared with the rhythms of a single night. In that awareness, you can allow your attention to loosen, letting immediate concerns fade while the larger, steadier patterns of the Milky Way continue quietly in the background. The Milky Way is one galaxy among many. When we look out into space with powerful telescopes, we see that the universe is filled with galaxies of different sizes, shapes, and histories. Some are large spirals with well-defined disks and arms, not unlike our own. Others are smooth, rounded ellipticals, where stars move on more random orbits and where little cold gas remains. Still others are irregular, with patchy distributions of stars and gas that do not fit neatly into simple categories. The Milky Way belongs to this wider population, a single member of a vast community of galaxies spread throughout space. Our galaxy is part of a collection known as the Local Group. This group includes two other large galaxies, the Andromeda Galaxy and the Triangulum Galaxy, along with many smaller dwarf systems. The members of the Local Group are bound together by gravity, moving within a shared region of space even as the universe as a whole expands. Each galaxy in the group has its own internal structure, its own stars and gas, and its own history of formation and interaction. The Milky Way is not central to the Local Group in any privileged sense. It is one of the more massive members, but not the only one. Looking at other spiral galaxies provides a kind of mirror for understanding the Milky Way. From the outside, their disks, bulges, and halos can be seen directly. Spiral arms wrap around their centers, dust lanes trace the locations of gas, and star-forming regions appear as bright knots along the arms. By studying these galaxies in detail, astronomers learn how disks form, how bars develop, and how gas flows through different regions. Many of the patterns observed elsewhere are applied to the Milky Way, helping to confirm and refine our models of its structure. At the same time, each galaxy in the universe has unique features. Differences in mass, environment, and merger history shape their appearances. Some galaxies show strong central activity powered by their central black holes, while others, like the Milky Way at present, are quieter. Some have experienced recent major mergers that have disturbed their disks, while others have evolved more gently. The Milky Way's current structure reflects its particular path through cosmic time, the amount of gas it has retained, the satellites it has absorbed, and the interactions it has undergone. Beyond the local group, galaxies cluster into larger associations and filaments, separated by wide regions where very few galaxies are found. On those scales, gravity draws galaxies together into clusters and superclusters, forming a web-like pattern that extends across observable space. The Milky Way occupies one point in this network. Its position is not central or special, but it is stable. It moves with other nearby galaxies as part of this large-scale structure, following paths set by the combined gravity of visible matter and dark matter on cosmic scales. Seeing the Milky Way in this broader context can change how it feels to think about our galaxy. Instead of being an isolated structure, it becomes part of an interconnected arrangement that stretches far beyond what is visible from Earth. Yet this does not reduce its significance for us. The Milky Way is the environment in which the Sun formed, where Earth orbits, and where the stars we see each night reside. Other galaxies demonstrate that systems like ours are not rare, but they do not replace the Milky Way's role as our immediate cosmic home. From here, inside one spiral arm of this galaxy, the larger universe is both distant and continuous. Light from other galaxies takes millions of years to reach us, crossing the space between groups and clusters. That light carries information about how galaxies like the Milky Way form, change, and relate to one another. In turn, understanding those distant systems helps clarify the story of our own galaxy. The Milky Way is one example among many, but for us it remains the framework within which the night sky, the sun, and the familiar patterns of stars all find their place. The Milky Way is large enough that ordinary comparisons fall short. Numbers such as tens of thousands of light-years in diameter and hundreds of billions of stars describe its scale in precise terms, yet they do not easily translate into a clear feeling. Rather than trying to imagine its full size at once, it can be more useful to think of the galaxy as something that sets a very slow and steady background for everything that happens on smaller scales. The distances between its main components, the time it takes for stars to orbit the center, and the cycles of star formation and stellar aging all unfold at a pace that is gentle compared with the rhythms of a human life. Daily concerns operate on much shorter timescales. Hours, days, and weeks are filled with tasks, decisions, and changes. Events can feel urgent because they arrive and pass quickly. Against this, the Milky Way provides a frame that barely shifts. While a busy day begins, unfolds, and ends, the Sun advances only a tiny fraction along its galactic orbit. While generations follow one another on Earth, the overall structure of the disk, bulge, and halo remains recognizably the same. The galaxy is not frozen, but its rate of change is such that it can be treated as fixed for any single lifetime. This contrast in timescales can help soften the sense of pressure that short-term events sometimes create. When you remember that the environment in which all of this occurs is so stable, it becomes easier to see individual moments as part of a wider pattern. The Milky Way does not respond to sudden changes in mood, weather, or circumstance. Its rotation does not speed up or slow down in response to what happens on Earth. It continues at the same measured pace, holding its structure while smaller processes play out within it. Thinking about this does not require you to hold the whole galaxy in focus. It is enough to picture the idea of a large, ordered system surrounding you, acting as a quiet reference. You are on a planet that orbits a star, and that star follows a smooth path within the disk of the Milky Way. The same physical laws that keep your feet on the ground also hold the galaxy together. Gravity pulls, light travels, and matter moves according to simple rules that do not change from one day to the next. This consistency supports a sense of reliability beneath the variation of daily life. As your body begins to rest, you can let this sense of scale work in the background. Breathing slows, thoughts become less tightly connected, and the details of the day start to loosen their hold. Above all of that, the galaxy remains in place, its stars following their quiet orbits, its gas flowing slowly through the disk, its halo extending outward in a way that does not depend on your attention. You do not need to solve or manage any part of it. You are already inside it, carried along by its motion without effort. If you notice your mind returning to small questions or unfinished tasks, you can gently set them against this larger frame. They belong to a brief interval in one small region of one galaxy. The gravity that holds the Milky Way together is the same gravity that keeps you lying where you are. The calm rotation of the galaxy, invisible yet constant, can be treated as a reminder that not everything requires immediate action. As you allow that thought to settle, you can give yourself permission to let wakefulness ease, knowing that while you sleep, the Milky Way will continue its quiet, steady motion around you. When we describe the Milky Way, it can sound as though every part of the galaxy has been measured and fixed in detail. There is a central bulge, a rotating disk, spiral features, a halo, dark matter, satellite galaxies, and a clear pattern of motion. Yet this picture, while coherent, is not complete. It is built from observations that have limits, and from models that carry assumptions. Understanding the Milky Way means recognizing both what is well established and what remains uncertain, without turning either into something more rigid than it really is. Some aspects of the galaxy are known with high confidence. The existence of the disk and bulge, the approximate size of the Milky Way, and the broad pattern of its rotation are supported by many independent lines of evidence. The presence of a supermassive black hole at the center is confirmed by precise measurements of stellar orbits. The need for dark matter to explain the rotation curve appears in observations of both our galaxy and many others. These elements form the backbone of our current model. They are unlikely to be overturned, even if their details are refined. Other aspects are measured less directly. The exact number of stars in the Milky Way is not known. Estimates rely on sampling and modeling, and they change as methods improve. The detailed shape of the dark matter halo, the precise distribution of mass in the disk, and the full history of mergers and interactions are subjects of ongoing study. Different models can reproduce the same broad observations while diverging in these finer points. In such cases, astronomers compare predictions, look for new data, and gradually narrow down which descriptions fit best. There are also regions that remain difficult to observe. Dust and gas obscure some lines of sight in visible light. Crowded stellar fields near the center pose challenges for separating individual stars. The far outer halo is faint and sparsely populated, making it hard to map. Future instruments, new wavelengths, and improved analysis techniques will extend what can be seen, but there will always be practical limits. The map of the Milky Way is therefore detailed in some parts, approximate in others, and incomplete in a few. This mixture of knowledge and uncertainty is not a flaw. It is a normal part of scientific understanding. What is important is that the boundaries between the two are kept clear. Supported results are presented as such. Hypotheses and models are identified as provisional, open to revision when new data arrive. In this way, the description of the Milky Way remains flexible enough to incorporate new findings without losing its overall structure. The galaxy itself does not change when our understanding does. Our picture of it becomes sharper, but the underlying system continues as before. For someone listening, it is not necessary to track which measurements are precise and which are approximate. It is enough to know that the Milky Way is described through careful observation, and that scientists distinguish between what is firmly known and what is still being explored. The galaxy is not an uncertain place in the sense of being unstable. It is a stable place that we are learning about gradually, starting with its most obvious features and moving outward into finer detail. Thinking in this way can make the idea of uncertainty less troubling. Not knowing everything about the Milky Way does not prevent it from being a calm, ordered environment. The parts we understand already show that its large-scale behavior is slow, regular, and governed by clear physical laws. The parts we do not yet fully understand sit within that same framework, waiting to be clarified. You can allow the limits of knowledge to exist without needing to resolve them. The galaxy does not require complete description to maintain its structure. It continues to revolve quietly, whether every detail of its composition and history has been mapped or not. The Milky Way is sometimes imagined as a destination, a place out there to which one might travel. In reality, It is not a remote goal beyond our surroundings. It is the environment in which everything already occurs, every star visible in the night sky, every orbit of the planets, and every path taken by light from distant parts of the galaxy all belong to this same system. There is no boundary to cross in order to enter the Milky Way. You are already inside it, in the same straightforward way that a person standing outdoors is already inside Earth's atmosphere. This perspective changes how distance feels. When people speak of going to the galaxy, it suggests that the Milky Way is separate from the place where they are. But Earth, the Sun, and the nearby stars are all components of the galaxy. Moving from one region to another within it does not mean leaving the Milky Way behind. A spacecraft traveling to the outer planets, or even beyond the solar system into interstellar space, remains within the galaxy's gravitational field. The environment changes gradually with distance, but the larger structure is continuous. Thinking of the Milky Way as an environment also clarifies the role it plays. It does not function as a destination with special conditions that must be met upon arrival. Instead, it sets the background parameters for what is possible locally. The distribution of stars and gas, the strength of the galactic gravitational field, and the presence of dark matter all contribute to the conditions under which solar systems form and evolve. Earth's orbit, climate history, and long-term stability are influenced indirectly by this wider setting, even though daily life does not depend on noticing it. The Sun's place in one spiral feature of the disk is a straightforward example. Our star is not parked at the edge of the Milky Way, preparing to cross into it. It is one of many stars embedded in a rotating structure of gas and dust. The spiral arm is not a road to a distant site, but a region where matter is slightly more concentrated, where star formation has occurred more actively. To exist here is simply to occupy one part of a large, layered system, the way living in a valley is to occupy one part of a continent. Seeing the galaxy as environment rather than destination can also reduce the sense that it is something separate from ordinary physical laws. The same gravity that governs the motion of a falling object on Earth governs the motion of stars around the galactic center. The same behavior of light that makes shadows and reflections in a room determines how starlight travels through interstellar space. There is no change in the rules when moving from a local scale to a galactic one. Only the distances and times involved become larger. In this view, the Milky Way is not a place to be reached, but a context to be recognized. Its disk, bulge, halo, and satellites form the stage on which smaller systems, such as solar systems and planets, follow their own paths. The galaxy does not have to be visited. It is the setting that already includes the ground under your feet, the sky above, and the star that provides the light and warmth for life on Earth. Across all of its scales, the Milky Way presents a pattern of quiet continuity. Stars form, shine, and eventually change into other states. Gas flows through the disk, sometimes collecting into clouds, sometimes spreading more thinly. Satellite galaxies orbit, lose material, and in some cases merge. The dark matter halo continues to provide the background gravity that holds the system together. Each of these processes has its own tempo, yet all are coordinated by the same underlying physical laws. Nothing stands outside this framework, and nothing needs to be added from beyond it to keep the galaxy functioning as a coherent whole. From a distance, if such a view were possible, the Milky Way would appear almost unchanging over short intervals. A snapshot taken now and another taken a human lifetime later would look nearly identical. The spiral pattern, the central bulge, and the faint halo would all be present in both, with only the closest inspection revealing subtle shifts. Inside the galaxy, the situation feels more detailed, but the same principle holds. Orbits continue smoothly. The distribution of stars and gas changes slowly. Patterns persist long enough to be treated as fixed for the purposes of daily life. This continuity does not mean that nothing new ever happens. On small scales, there are always local events. A region of gas may become unstable and begin to form stars. A massive star may reach the end of its life and release energy into its surroundings. A satellite galaxy may pass slightly closer or farther away on its orbit. These events are real and measurable, but they occur within the larger, stable structure of the Milky Way, rather than disrupting it. The overall gravitational field adjusts gently, accommodating such changes without losing its basic shape. The galaxy's predictability comes from the regularity of the laws that govern it. Gravity acts in the same way on a cluster of galaxies as it does on a falling object on Earth. Light travels at the same speed between stars as it does across a room. Matter follows the same rules of motion and interaction whether it is part of a gas cloud, a star, or a planet. Because these laws are constant, the Milky Way's long-term behavior is steady. Models based on them are not arbitrary guesses. They are extensions of principles tested in many different contexts. For someone considering the Milky Way while lying still, this constancy can be a quiet reassurance. The galaxy does not depend on attention to continue. Its rotation does not require supervision. The stars do not need to be watched to keep them in their orbits. Whether thoughts are busy or calm, the larger structure persists. The disk turns slowly around its center, the halo extends outward, and the satellites continue their long paths. You do not need to hold any of these details firmly in mind. It is enough to keep a simple picture, a large, ordered system surrounding you, changing only gradually over spans of time far longer than a single life. Within that system, your own experiences occupy a small, finite interval. They are real and meaningful, but they do not alter the steady background. The Milky Way will maintain its quiet continuity as you move from wakefulness toward rest, its slow, stable patterns continuing whether you are thinking about them or allowing them to fade gently into the background. As you come to the end of this quiet journey through the Milky Way, it can be helpful to let the details soften and fall back into a simpler idea. You are on a small planet that orbits an ordinary star. That star is one of many in a rotating disk of gas and dust, wrapped around a central bulge and surrounded by a faint halo. The whole structure is held together by gravity, both from the matter we can see and from dark matter that reveals itself only through its pull. This galaxy is not a remote object. It is the place in which every night, every sunrise, and every familiar pattern in the sky quietly takes place. The galaxy does not ask for attention. Its rotation continues whether or not anyone is thinking about it. Stars follow their paths around the center. Gas clouds drift, condense, and sometimes form new stars. Old stars return material to the interstellar medium. Satellite galaxies orbit on wide curves. All of these motions proceed at a pace that is slow compared with individual lives, yet steady when viewed across longer spans of time. The Milky Way has been present for billions of years and will remain long after this moment has passed. Within that large structure, life on Earth and the events of human history occupy only a very thin layer. Days, weeks, and years pass, while the Sun moves only a small distance along its galactic orbit. Personal experiences begin and end while the disk keeps its shape and the halo retains its quiet extension. This does not make those experiences unimportant. It simply sets them against a wider background in which change is real but not hurried, and in which the physical rules remain constant. If you picture the night sky now, you might imagine the soft band of the Milky Way arching overhead, even if there are walls and ceilings between you and the open air. Beyond those obstacles, above clouds and scattered light, the combined glow of distant stars still traces the plane of the galaxy. The same gravitational field that holds those stars in their orbits also keeps you resting where you are. The same behavior of light that carries starlight across thousands of years also carries gentle illumination into the room. You are not separate from the processes described in this story. You are already inside them. As your breathing slows and thoughts become less tightly arranged, you can allow the image of the galaxy to become simpler still. It can shrink to the feeling of being in a stable place, surrounded by a structure that changes only gradually. You do not have to remember every term or picture every component. It is enough to know that the Milky Way will continue its calm rotation while you sleep, holding stars, gas, dust, and dark matter in a consistent pattern that does not depend on your awareness. If sleep comes soon, it will arrive in a universe that remains orderly in your absence. If it takes longer, that is completely fine. You can rest in the knowledge that you are lying on a planet within a solar system, quietly carried along inside a galaxy whose slow, steady motions form the background to all your shorter rhythms. We from Sleepy Stories wish you a good night.